Bam, that's true. In the next couple of videos, we're going to be talking about in calculus a concept called related rates. Remember when we started studying calculus, we talked about how with the idea of limits, we were allowed to bring motion, or able to bring motion into all the static measurements that we had all the way up to pre-calculus. One of the examples we're going to take a look at is going to involve, a couple of them actually, but the one specifically is going to involve a right triangle. And what I mean by related rates is this. You're on the side of the road. Okay? The road is right there perpendicular. And at least it will be in our diagram. And you're looking down the road and you see a car coming. You can look at that car and really pretty much not have to move your body or your eyes or whatever. You're not going to have to move very much to keep that car in view until it starts to get close. And the closer that car gets, the more that distance from you is reduced, the faster that you're going to have to rotate to keep it within your field of view. Now with your eyes, it kind of just happens. But if you ever seen, I'm a big racing fan, and you'll see like the photographer standing by the side of it, and actually I've taken some of these pictures. I'm going to post one down here in the corner of the screen just to share my work. You're kind of standing there and you're like, and all of a sudden it's like, okay, and then you go back and it's like slow, 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 and you got to pan really fast to keep it within your view, vision of view as it becomes closer and closer and closer. So that distance is somehow related to how fast you're having to rotate to keep it within your view and get the shot. So that's what we're going to, that kind of idea. Of course, there's many scenarios. It's real world problems, so every problem could be different. Hopefully your textbook's not making every single question different. Otherwise you'll probably have a hard time completely grasping the concept. But at any rate, I'm rambling here. Let's take a look at the 4 steps and do our examples over the next couple of videos. First step, guides for solving related rate problems. Identify all given values and all values you need to find, and then sketch a diagram. It's always helpful to get, that sketch will help you place the variables in the right place, and once you get a numerical answer, if you make a reasonable sketch, you can use that to determine if the number that you found is reasonable. Write an equation involving all the variables of interest. Remember, the rate of change of variables will, or the rate of change variables will not be seen until you use the central or the chain rule to implicitly differentiate both sides of the equation with respect to t. Now, why t? T is time, right? If you're driving a car, you're either measuring your speed in miles per hour or kilometers per hour. Your motion problems are going to be related to time. How fast is something going? How fast is something spinning? What's the linear, like when trigonometry we studied linear and angular speed. That was distance over time or amount of ratings over a given period of time. And then finally substitute in your known values of change and any other variables you have that you still haven't plugged in, and solve for the last remaining variable of interest. So let's get this out of the way, these directions, and start looking at some examples. And they will be in increasing difficulty as we go through these. So if you're struggling with this initial concept, of course, maybe the first couple of videos or examples, will be fine. And we will get them to be more and more involved and more difficult as we go. So let's see what they look like. Bam! So here's our first example. An object is moving along the given path of y equals parentheses x minus 1 squared plus 3 with a horizontal speed, left and right, of 16 meters per second. Find the vertical speed at x equals 0, x equals 1, x equals 2, and x equals 3. So I gave you the equation of a parabola. The vertex is at 1, 3. Now, when we're to the left of the parabola, as we read this left to right, the graph is falling, of course. And the closer that it gets to the vertex of the parabola, you can see that a parabola will come down very sharply. So its speed is very negative, very quickly falling. And then it starts to slow down until eventually it flattens out and the horizontal speed is going to be 0 at the vertex. And then it starts to accelerate back up the other side of the parabola. So the vertical speed is going to be changing. It's going to be different at these values of x. We also have a vertex at the x value of 1. It's actually, again, like I said, 1, 3. So we should be expecting this speed to be negative this vertical speed to be 0, this vertical speed to be positive, and because of the symmetry of the parabola, they should be the same speed, only with different signs, just to, kind of let you see that. And then at the x value of 3, as we start to, curve upwards, the vertical speed should be accelerating. Now, I've given you the values of, I've already sketched it for you, given you the equation, and I've given you the values of 0, 1, 2, and 3 for x. I also gave you here where it says the horizontal speed is 16 meters per second. Well, that's a rate of change. Now, it's rate of change over time. So this is going to be the derivative of x over, or the derivative of x with respect to time, or the horizontal distance, because the x-axis is a, well, your horizontal axis, right? So that's how fast you're moving along the x-axis with respect to time. So dx over dt is going to be 16 meters per second. Now, right now I've got a parabola, it's got the equation. I don't have any variables related to change. I don't have any derivatives. So we're going to take this equation, find the derivative implicitly, find the derivative of both sides of the equation implicitly with the, in relation to time, in respect to time. So we're going to take the derivative of y is, well, if it was the derivative of y with respect to y, it would just be 1. If it was the derivative of y with respect to x, like we've been writing recently, it'd be dx over dy. But now it's in relation to time, or in respect to time. So this is going to be the chain rule. We're going to take the power of 1, drop it down up front. This comes to be 0, so this really is just going to be dy over dt equals, now here we can see more like a natural idea of chain rule. It's an inside function and a power of 2. So it's going to be 2 brought down up front, the general power rule is going to be 2 times x minus 1. This power is going to be reduced to a value of 1, which we don't need to write. I'm not going to write it because it's going to be a prime symbol. And then we have to find the derivative of the inside function. Well, if you're finding derivative with respect to x, this would just be 1. That's a constant, so it's 0. And the derivative of x with respect to x is dx over dx, which is 1. But we're finding the derivative with respect to time. So this is also, the x isn't going to just sort of like go away like it has been with our implicit differentiation. It's going to be the derivative of x with respect to, again, time. Well, now, this is, again, like I said, we're going to go from easy to hard. So this is it. This is what I got. We're looking for the vertical speed. So I'm looking for dy over dt, change in y. That's a vertical change. That's vertical speed. dx over dt, that's the 16. So all we really have left to do is, well, let me write this final answer. dy over dt is equal to 2 times x minus 1 times 16. Or that's going to be 2 times 16 is 32 times x minus 1. So that's dy over dt. Now that I've got my equation solved for my variable of interest, just plug in, my 4 given values of x and see what we get. So let's say that x equals 0. Well, then dy over dt is equal to 32 times 0 minus 1, or negative 32 meters per second. Make sure I'm not saying something silly here. Okay, and it should be negative because the graph is falling to the right. Let's let x equal 1. That's where the vertex is, so we should be getting a value of 0. So dy over dt is 32 times 1 minus 1, and indeed that does come out to be 0, which it should have. We have symmetry in this parabola, so when we go to use the value of 2, we should have that 32 show up again, but only be positive this time, because we are rising up to the right. So x is equal to 2. So dy over dt is equal to, where are we at here? 32. Probably in the way of the writing here, times 2 minus 1, and indeed that is positive 32 meters per second. And then finally, when we let x equal 3, we have dy over dt is equal to 32 times 3 minus 1, or that's 2 times 32, which is 64 meters per second. And that's the end of our first example. Next example. For our next example, we have a problem that sounds very similar. Find the rate of change of the distance between the origin and the moving point, now that part's not the same, on the graph y equals 1/2 x squared plus 2. If dx over dt, the horizontal speed, the rate of change horizontally, is equal to 4 units per seconds, whatever. Okay, well, first of all, I have not given us specific values of x. We're not going to find the rate of change at specific given values of x. We're just going to find an equation that describes the rate of change. So that'll be a little bit different, but the biggest deal here is the previous example asked for the change or the rate of vertical speed. They asked for dy over dt. How quickly is the point falling or rising in respect to the x-axis? What was dy over dt? Here, I want the rate of change between a point and the origin. So I don't want to find a vertical distance. So I don't need or don't want to see dy over dt because that's just the vertical rate of change. I want the rate of change from the point to the origin. It's a slanted line. So I can't just take this parabola and find the derivative of both sides implicitly because I'm going to have dx over dt on one side and dy over dt on the other, and I don't want the vertical rate of change. I want the rate of change of the distance between the point and the origin. Now I keep saying the distance, right? So that means I need to use the distance formula. I'm going to use the equation of the parabola, but I want the rate of change between the point and the origin. That slanted line requires that, to find that distance, requires use of the distance formula. So, d is equal to the square root of x sub 2, or the x from the point, minus x sub 1, the origin. So it's going to be x minus 0 squared plus y minus 0 squared. And that's going to simplify to be x squared plus y squared. This describes the distance between any point, or this point, and the origin. Okay, I can write this as d equals the square root of x squared plus y squared, and I don't like finding derivatives with a square root symbol, so I could take this and write it as a set of parentheses and have it to the 1/2 power, and I can find the derivative of this equation implicitly, but there's a couple of problems there. One, I will have the change in distance in respect to time, or d over dt. I will have, through the chain rule, dx over dt, which I'm given, but I'm going to have dy over dt. And nowhere in here, this problem, am I given a rate of vertical, a rate of change, a vertical rate of change. Secondly, if I go try and find the derivative of this, what am I doing? Just completely ignoring the equation of the parabola? I'm completely ignoring the actual path that point is following. So I got to put these together. I got to put the distance formula together with the formula of the parabola so that they're actually related to each other. And I need to keep in mind that I'm only given dx over dt. I'm only given the horizontal speed. So I don't want to see a dy over dt after I'm done finding the derivative because I don't know what that is. So we need to do some kind of substitution with this equation of the parabola, and after all it's the path that the object is following, with the distance formula. And I need to do it in such a way that I only have x's left, so that after I find the derivative, I'll have only dx's over dt's, because that's what I'm given and that's what I have to use. So that means that we're going to, before we find the derivative, take this y squared out, or take the y out and replace it with what it's equal to from the function. So this is going to be equal to the square root of x squared plus 1/2 x squared plus 2 squared. Okay, let me make sure I'm not writing something silly here and I do a whole problem with a mistake in it. Okay, good. So I got to work this out a little bit and then simplify it. So d is equal to the square root of x squared plus, we're going to have to FOIL this binomial out. Do we really need to do it now? We don't have to do it now, but my notes have it where I have. So I'm going to go ahead and let's FOIL this out. So we got 1/2 x squared plus 2 distributed out. 1/2 x squared plus 2. So that's going to be 1/2 x squared times 1/2 x squared is 1/4 x to the 4th. 1/2 of 2 is 1, so we have plus 1x squared. And another 1x squared. And then 2 times 2 is equal to 4. So this is going to be, let's see here, 1/4 x to the 4th power. 1 and 1 makes 2. And then the 4. Let's simplify this up some more because here's a 1 and here's a 2, which makes 3. They're like terms. So we have d is equal to the square root of 1/4 x to the 4th. 1 and 2 makes 3, so plus 3x squared plus 4. And we're going to find the derivative, and I don't know why I keep writing this radical sign, because it doesn't make finding derivatives that friendly, so let me erase that. And write that as the 1/2 power. Now, we're going to find the derivative of both sides with respect to t. So, we get dt is equal to, this is general power rule, so we're going to take the 1/2, move it out front, so 1/2 times 1/4 x to the 4th plus 3x squared plus 4. We're going to reduce this by 1/2 and get negative 1/2. Then inside, we've got 1/4 times 4 is 1, so we have x to the 3rd. Now, we are now finding the derivative of the inside function. So, remember we're doing the derivative with respect to t, not x. So this isn't going to just be x to the 3rd. It's going to be x to the 3rd dx dt. Plus, bring this down, 3 times 2 is 6. So 6x dx dt, the chain rule there. This is a constant, so that's 0. Now, we have got, let's see here, we've got the derivative with respect to t of, this is going to come down to the bottom, so we have 1 over 2 times the square root of 1/4 x to the 4th plus 3x squared plus 4 times x cubed dx dt plus 6x dx dt. Sorry for the interruption there. So now we've got 1 over 2 square root of all this stuff. Over here we've got x cubed dx dt plus 6x dx dt. We've got a lot of variables going on here, but we know what dx dt is. It's equal to 4. So I can take these values out, and I'm going to erase this because I'm running out of room here. We're going to take out the dx dt and plug in what it's equal to, which is dx over dt is equal to 4. So we're going to plug in those 4 values, those values of 4, and write our final answer, which is going to be d over dt, the change in the distance between this point and the origin with respect to time, is going to be equal to 4x cubed plus, now 4 times 6 is 24, so plus 24x over the 2 times the square root, I'm running out of room here, 1/4 x to the 4th plus 3x squared plus 4. Now, this radical sign is grouping all that stuff together in the denominator, and the multiple of 2 is out front. Now, both of the terms on the numerator, or in the numerator, are also even. So we can cancel a 2 out here and write our final answer as 4 divided by 2 is 2, so 2x to the 3rd 24 divided by 2 is 12, so plus 12x over the square root of 1/4 x to the 4th plus 3x squared plus 4. And we have the dt, d over dt, the change in the distance between that point on the parabola and the origin given to us by this expression. Now, we can take any value of x we like, plug it into that expression, and it'll, let us plug in any value of x, so it'll tell us basically we can pick any point along the curve we like, and this formula will tell us how quickly that point is, what the rate of change is, how quickly it's approaching the origin with that horizontal speed being 4 units per whatever period, measurement of time you're using in the problem. So, let's get to the next one. Bam! Alright, last example we're going to do in this video. The next video, I'm going to have 3 examples, the last 2 of which are going to be involving rate of change for rotation, or rotational rates of change. Here we have a conical tank that's 10 feet across and 20 feet deep. If the water is flowing into the tank at a rate of 8 cubic feet per minute, find the rate of change for the depth of water, when the water itself actually is 10 feet deep. There's very, very sharp, pointy bottom here, so as you start pouring in water, the level is going to rise very, very quickly until, but as the cone opens up and you have more volume to fill out horizontally, the rate of change for the rise or the depth of the water is going to start to slow as it widens up. So it's going to be varied. So when the water is 10 feet deep, how quickly is the level of the water rising? How quickly is h changing? What is the rate of change for h, the depth? Well, we have the volume of a cone. We have volume is equal to pi over 3 times r squared times h. And I can find the derivative of both sides with respect to time, and that would be dv over dt is equal to, bring the 2 down and get 2 pi over 3r dr dt. Everything involves the chain rule because we're not finding the derivative with respect to any kind of variable that's in the equation. And then the derivative with respect to time of h is simply dh over dt. Well, I'm just trying to do this in a way that points out all the little faults that I think you might be having as a student. And what's the problem with this? We're being asked to find dv over dt. Well, that's the change in volume over time, and I've been told that we're putting in 8 cubic feet per minute. So dv over dt is equal to 8 cubic feet a minute. So I have something to put in here. We have the radius. Well, if I know that the depth is 10, we're going to be setting up similar triangles here in a second. There's other ways to figure it out as well, but I've got a radius of 5 and a depth of 20, so there's some kind of constant ratio going on with the sides of this cone. We'd call it slope because it's straight on the sides. And so I can set up a similar ratio setup to find out what the radius should be when the depth is 10. 20 divided by 2 is 10, so 5 divided by 2, that'd be a radius of 2.5. dr over dt and dh over dt. Well, dh over dt, that's the change, the rate of change in the depth. That's what we're looking for. But nowhere in this question does it ask how quickly the radius is changing, and nor am I given that value. So actually, I don't want the variable h or r, excuse me. I don't want the variable r in this equation because I'm not given any information about the rate of change for the radius, nor am I asked for it. And I'm also not given this variable, so I can't plug it in, and I would have 2 unknowns in the same equation, and that would be a little difficult. So what we're going to do is we're going to start over, and we needed to figure out some kind of relationship, another related rate type thing, here with, we're already relating, the volume with the height and depth and all the other good stuff, but I don't want r and h in here at the same time. The question is about find the rate of change for the depth of the water when the water is 10 feet. I want dH over dt. I don't want dr over dt. So this is going to have to come out. And we can see that the radius is equal to 1/4 the height here. But if the question had a slightly more complicated numbers, you'd want to maybe step off to the side and figure this out. We have a height of, well, we have a height of 10, but this problem has motion in it, and I don't really want to use the value of 10. I want to say that h over 20 is equal to, let's see, this unknown height of h. I mean, we know it's specific to 10 for the problem, but we have a variable measure of h over 20, the maximum height we can reach. We have a variable radius measurement over 5, so r over 5. We cross multiply this, we get 5h equals 20r, and we divide both sides by 5, and we get h is equal to, except I don't want to get rid of h, I want to get rid of r, so let's try that again. We divide both sides by 20, and we get 1/4 h equals r. See, I don't want to plug in the 10 because I want an equation that relates the radius to the height, because I need to use that in my formula. So the r is going to come out, and in place of r, I'm going to put in 1/4 h. So this is equal to pi over 3 times 1/4 h squared times h. And 1/4 squared is 1/16, so that's going to be equal to pi over 3 times 1/16 h squared times h. And now my volume is equal to pi over 3, h to the first times h to the second is h to the third. So we have h to the third, and let's not do this pi over 3 thing here. 3 times 16, 3 times 10 is 30, 3 times 6 is 18, so we have 48 as our denominator. So you see, the measurements of the entire cone are important because I really only care about what's happening with the water, but the shape of the cone is allowing me to make this relationship between the radius and the height. And that way I can manipulate the equation to kind of make it a little bit simpler, have fewer variables in it, and thus be able to solve the question. So here we have volume. We're going to find the derivative of both sides with respect to t. So dv over dt is equal to 3 times pi over 48. That's going to be 3 over 48. 3 over 48 reduces to be 16. So we have pi over 16 h squared. And it's a chain rule. We're just, again, the derivative with respect to time. So dh over dt. Now, we are given the rate of change for volume. That's 8. We got pi over 16. We have h squared. Well, we're told we want to know what the rate of change for the depth of the water is when the water is specifically 10 feet deep. And we have, again, dh over dt, which is that rate of change we're looking at, the rate of change for the depth. So we have 100, because that's 10 squared, so we have 8 equals 100 pi over 16 times dh over dt. That means that dh over dt is equal to 8 times 16. Let's see here. 8 times 10 is 80. 8 times 6 is 48. 80 and 48 is 128 over 100 pi, and this is reducible, but I'm going to go ahead and give you a decimal version of that. And, well, I would if my notes were correct. Hold on just a second. Sorry for the little bobble up there. 128 over 100 pi reduces to be 32 over 25 pi, which comes out to be 0.407 feet per minute. I hope this helps. If not, my next video is going to again have 3 more examples, the last 2 of which will be dealing with angular velocity. And hope you enjoyed the video and it helped. I'm Mr. True. Bye! Go do your homework.